energy of sodium. Now that means I no longer have this one outermost electron. So once sodium becomes Na+, then that means now I'm about to take, and if I ionize it again, I'm about to take an electron from its core. As soon as I took the one electron away from sodium, it was stable, its octet is now full. Second ionization energy of sodium is 4,562 kilojoules. Dramatic difference from the first ionization energy level. And why? It's because I'm going to need to supply a lot more energy before I'm going to be able to take an electron away from an atom that is stable now. So because that outer shell is full for sodium, for the sodium ion, Na+, I'm going to have to give it a lot of energy to remove one more electron, and that's what I see. So a lot of times we can predict charges. If I gave you a chart like this, it's really easy to predict the charge of an element or of an atom just because we can find where the jump is in ionization energy, and then we know how many valence electrons it has. So I don't need a lot of energy to get off the first electron, but then to get off the second one, I see this huge jump. So that means that if I were looking at this and I didn't have the elements, I would think that this then would have just one valence electron. And it does, because we know that that's sodium. So let's look then at the next one. Ionization energy of the first one is 738. The second one is 1451. The third one is 7,733. Huge jump. So I went from a big jump between 1451 to 7,733. So that's telling me I don't need as much energy to take off the first two valence electrons, or these first two electrons. I need a lot of energy to take off the third. So that means that now I'm taking off a core electron here. So that means that this element should have, or this atom should have, 2 valence electrons. We know that it does because it tells me right here that that's magnesium. So that's another way that you can read this. And that's, I think, how AP Chemistry will want us to read a graph like this. Next one is aluminum. I know aluminum has 3 valence electrons, so technically I should have 3 ionization energies that are, relatively increasing from one another. And then the fourth one should be a huge jump between 3 and 4, and I see that. So not as much energy for the first one, a little bit more energy for the second one, a little bit more energy for the third one, but then as soon as I hit that core electron, it's 11,577 kilojoules there. So you get the trend. Okay, 3 elements are indicated in the periodic table below. Which one has the largest second ionization energy? Which one has the largest second ionization energy? Okay, you tell me which one you think that it is, and then we'll check tomorrow. So trends in first ionization energies, and really the trends should be fairly similar for second, third, fourth, so on and so forth. So for first ionization energy trends, as one goes down a column, less energy is going to be required to remove the first electron. So as we're going down a group, as we're going down a family, so let's just go down from hydrogen through then the alkali metal family. Or if we go down the halogens, fluorine to iodine. It's going to take less energy. And why is that? It's because there's less Coulombic attraction between the outermost electrons, the valence electrons, and the nucleus. I've added more energy levels, there's more shielding, thus there's a lesser attraction between those outermost and the nucleus. So that's why we see it to be lessened as we go down a group. Generally, as we go across a row or as we go across a period, it's going to become harder to remove an electron. So ionization energy as we move from left to right should increase, and that's because I'm going from metals, which typically form cations, so I'm going from metals over here, typically forming cations, to nonmetals, which are seeking electrons to fill that outer shell, and things that really ultimately want an electron. So it's going to take a lot more energy to remove an electron here, which is why ionization energy would increase as we're going across. I need to apply more energy to these particular elements because they're not wanting to give up their electrons. And ionization energy is all about the removal of an electron. Okay, we do see that there are some discrepancies in this. And there's two of them, actually, or what we could call discontinuities. For the first one, we see a discrepancy between groups 2A and 3A. So specifically, I'm talking about from the alkaline earth metals here to the boron family. Guys, for the most part, we kind of forget about the transition metals in these trends. And that's just because, I mean, the increase is just so slight that for us, it's kind of negligible as we move across the periodic table. So transition metals will always just be like a factor that's just out for us. We don't have to worry about them. So group 2A being the alkaline earth metals, to then group 3A being my boron family. So we would think, since it's increasing as we go across, that the boron family should have higher ionization energy levels, or it would take higher ionization energies to get those outermost electrons off. But we actually see that to be the opposite. Alkaline earth metals have a higher ionization energy than the boron family. And why is that? That's because when I'm in the alkaline earth family, or I'm in the alkaline earth metals, ultimately what I see is that I know that I have the s orbital is full. It has the 2 electrons that it needs to be full. Boron family would then just have 1 electron in the p orbital, which kind of just creates instability because it's all by itself, versus taking away an electron from a stable orbital is going to take a little bit more energy. So that's why the alkaline earth metals are going to have a little bit of a higher ionization energy than the boron family, because I'm taking away an electron from something that's stable, versus the boron family doesn't really care if it loses that 1 from the p orbital, okay? I see the same similar trend between group 5A and 6A. So as I'm going from the nitrogen family to the oxygen family, they're very, very, very similar. They're very close. But there still is this discontinuity. And that's because for nitrogen, there's a sense of stability in knowing that each of my sublevels has an electron present, versus oxygen, I have more electron repulsion happening here because I have that extra electron now for oxygen that's just in one of those orbitals, versus nitrogen, which is nice and stable with 1 in each. So this electron repulsion is actually going to make it to where I don't need as much energy because oxygen inherently would prefer to get rid of that, okay? So that's just the discontinuity that we can see there. I would also like you guys to try to write for me, and I know you've done this before, so I'm not worried about this, but write the electron configurations for the following ions that we have here. We'll discuss and go over those tomorrow as well. Okay, last one, electron affinity. Now, electron affinity is the energy change that accompanies the addition of an electron to a gaseous atom. Okay, so ionization energy was the amount of energy that it takes to remove an electron. An electron affinity is the energy change that happens when an electron is actually added. It is not like electronegativity where it's just the attraction. It's the ability of an atom to attract an electron. With electron affinity, we are actually adding an electron to the atom. So that's the biggest difference between electron affinity and electronegativity. Electronegativity is the ability to attract the electron, and electron affinity is actually adding on the electron to the atom, okay? Biggest difference. Huge misconception in science is that when we break bonds, that means that we release energy. It is totally the opposite. When we break bonds, we need to supply energy. When we form bonds is when there is a release of energy. I am forming some type of new attraction when I add an electron to an atom. I am forming a Coulombic attraction. That is still technically a bond. A bond is just some type of Coulombic attraction. So electron affinities should typically be negative because that means I'm releasing energy, okay? So if I'm releasing energy, the addition of an electron, we usually see them to be negative, just so we're clear. If I want to show this using a reaction stance, then I could see that chlorine in the gaseous state can add on an electron to become the chloride ion. So it's actually taken on an addition of that one electron. And then we know from research that it will release 349 kilojoules per mole of energy. And it's negative because that's indicating that it's releasing that energy. It's releasing it. If it were positive, that would mean that it would have to have gained energy before it would have taken on that electron. So, for example, argon, if it were to take in an addition of an electron here, if it were to take on an electron, I would see that its energy level would actually be positive. It would be greater than 0. And if you think about that, it makes sense because ultimately noble gases, we know, aren't going to want to take on an additional electron at all. So they're going to have to absorb a ton of energy before they're going to even be able to hold that extra electron. They're going to have to make room or make space because those noble gases are fairly small in size. Okay, so guys, tomorrow, because this video is like uber long, so tomorrow we'll talk about this very last slide. You also have a couple other videos that you have to watch. I am so sorry that your videos are long tonight. Just forgive me tomorrow. I'll bring you food. Okay, bye.